Okay. So today we will do something exciting, very exciting. At the second half of the discussion. So by the end of the discussion. So like, please, if you can, stay to the end. Uh, so yeah, I mean, at least that's something that I feel excited about. So but without saying that, let's first mention some announcements. First of all, your homework 33, 34, and 35 is due on today at 11:59 p.m. Yeah, I noticed that a lot of you haven't submitted yet. I don't know why. Maybe because like I didn't pull up the tab earlier enough, but like definitely submit it tonight. And another thing is that homework 36 is due on Thursday at 11:59 p.m. So that's like something unusual. Like so homework 36 will be the last mandatory homework that is for grading purpose. So that which means that homework 37. So actually, there's no homework 37, and homework 38 is optional. Like the contents may still cover in final exam, but not for submission. The homework itself is not for submission. Yeah, so that's homework, and you should receive your score for quiz 12. So for quiz 12, the median is a 9 and the mean is a 8.26 on 12-point scale. Yeah, so and we will have a quiz 13 today, so it will happen very shortly. So in the meantime, you can check on Gradescope if you can access your quiz 12 and you can see your submission link for quiz 13. And also like, yeah, a lot of students are submitting their homework right now. So if you haven't submitted your homework, do remember to submit your homework. Okay, so yeah, I guess that's it for the logistics. Is there any question about logistics? All right. So we will jump into our for the quiz correction, like those who are open is like open, and for the thing that like for the other specific quiz correction, I'm still like I will definitely make announcements on Thursday about the situation, like whether there's enough response for the course evaluation or not. But just like stay tuned. Like don't be too worried about that. But like for quiz correction of 11 and 12, they are up on Gradescope. You can do it now. Yeah. So let's move to today's topic on the chi-square. So so there are two types of chi-square hypothesis testing. One of them are goodness of fit. The other one is test for independence. So maybe we can start with the goodness of fit test. So the objective of goodness of fit test is to test whether like is to test if I'm giving you like multiple outcomes and if like the multiple outcomes matches my expectation or not. So the idea is that for example maybe like I should start with an example in lecture. So in the example, professor talks about if we have a die, and our null hypothesis is to test if the die is fair, and our alternative, so like the die is six-sided, and the alternative hypothesis is the die is biased. So that's different from a coin. A coin you only have like the head and tail, and for a die you can have like 1, 2, 3, 4, 5, 6 value. So the idea is we do it for 60 times and check the result. So for that, we're using a chi-square test, and so we want to for this chi-square test of goodness of fit, we always need to draw a table. So the first column is the value, and that means the possible outcome. So in this case, this is a six-sided die. The possible outcome is 1 or 2 or 3 or 4 or 5 or 6. And an observed frequency. So say like we are given the statistic of our observed frequency. So we are given the 12, 1, 13, 12, 8, 3, 6, 4, 16, 5, and 5, 6. And but like remember, so that sums to a total of 60 rows, 60 flips. And then since it is a uniform distribution, like a row of 60 die, if we assume that our null hypothesis is correct, if the die itself is unbiased, that means it is a uniform distribution. So if I'm giving like 60 observations, each of observation, my expected value is 10. And then you want to find something called the difference square over expected value. So that's just observed minus expected. So EXP here, I'm short for expected instead of exponential, divided by EXP. So that'll be 12 minus 10 squared divided by 10, which is equal to 0.4. This will be 13 minus 10 squared divided by 10, which is 0.9. And 8 minus 10 squared divided by 10, which is 0.4. 6 minus 10 squared divided by 10 is 1.6. 16 minus 10 squared divided by 10, that is 3.6. And 5 minus 10 squared divided by 10, that is 2.5. So if you, so like for the chi-square test, we always need two values. So let me rephrase it in this way. For a chi-square distribution, the only parameter that affects this distribution is the degree of freedom. So only degree of freedom affects the distribution. For example, for degree of freedom equal to 1, the shape might be something like that. For degree of freedom equal to 5, the distribution may be something like that. So but like it's not an exact distribution, but what I'm saying here is like the only parameter that affects the shape of distribution is the degree of freedom. But there's another value called R statistic. This is just like something similar to the corresponding to the p-value. So that R statistic is like, given that I have already have a chi-square distribution of certain degree of freedom, how do I find the p-value corresponding to the R statistic? So that's kind of like the order is you first have the degree of freedom, and then you will have a distribution. And then you have the R statistic, so you can find the p-value and you can compare it with your significance level. Here, let's say significant value is 0.05. So what is R statistic? Back to our question, R statistic is just like the summation of the distance square over expected value. So the R statistic is just the summation of everything above. In this case, it would be 9.4. So what do we do next? We check the degree of freedom. So the degree, so let me write it here. R is equal to 9.4 here. And the degree of freedom is defined to be the order of the outcomes minus 1. So the order of outcomes means how many outcomes is there. So for a 60-sided die, there are 6 possible outcomes. Minus 1 is equal to 5. So our degree of freedom is 5. So next, we can look up the online software for solving this problem, or look up a chi-square table. So there's a link called from like Berkeley website, statistics.berkeley.java/html/chi-lit.htm. So this website provides you an online applet for calculating, for inputting like specific value of the chi-square, and then calculating the p-value versus the significance value. So that might be very helpful for today's discussion and for like your future calculations or your homework. So back to our example, we are given that we have a degree of freedom of 5. So we can input that degree of freedom 5 in the online applet, and that will give you a distribution similar to that. That's the chi-square at degree of 5, a degree of freedom equal to 5. And then we want to like implement, we want to input the R statistic to find the corresponding p-value. So here we are inputting R equal to 9.4. So the online applet will tell you the result that 9.4 is somewhere here. But like it doesn't fail. So it will tell you like the area here is 90.59%. So you'll know that the p-value is equal to 1 minus 90.59%, which in this case 0.0941. This is greater than our significance level 0.05. So we cannot reject null hypothesis. So that means like we cannot reject that the coin is unbiased. The coin is fair. So we will stay with our null hypothesis. Yeah, another way is that you can check the chi-square table, and you can see that the significant level, which is the boundary for rejection zone, at degree of freedom k equals to 5, and alpha is 0.05 for a chi-square test. It's 11.07. But we know that our R statistic is equal to 9.41, which is less than 11.07. So we don't have enough information for rejecting the null hypothesis. So either way, it works. So that's basically it. That's basically how you calculate the goodness of fit test for chi-square. So for all the rest of problems, as long as you want to use this problem, this test game, it's pretty much the same. You first um you first write out the null hypothesis and alternative hypothesis, and then you want to say like whether you are using the goodness of fit or not. If you are indeed using the goodness of fit, you form a table. The table will be outcomes, observed values, expected value, and difference square over expected value. And then you need two specific things for the category. One is degree of freedom, and the other one is R statistic. For degree of freedom, you can calculate it by directly compute how many possible outcomes you have minus one. And for R statistic, you do a summation over the degree, the last column of your table, which is difference square over expected value. So after you have these two values, you can either go to an online applet to input your results for the R statistic and degree of freedom to get your p-value, or you can check. So if you get a p-value, you can compare it with the significance level. Or you can check a chi-square table to find to look at the significant value, and then you will find the critical value. The critical value is the boundary of your rejection zone. Yeah, and then you can compare if your R statistic is bigger or less than the boundary of rejection zone, and see if it lands on the rejection zone or not. And last, you always need to give a conclusion. You will give a conclusion for the alternative hypothesis or not hypothesis, whether you are rejecting or not. So you need to like write it in the full process. You need to like for every step, it has a meaning on it. So either on the quiz or on the final exam, we are expecting you to write it very rigorously for each step by step. And quiz for today will be something what I'm just talking about right now. And I will leave you 1 minute for asking any question you have. And otherwise, I will upload the quiz right now. Okay, it is uploaded on Bcourse. You have 20 minutes to do the problem. So it will be due at 10:23 or 10:24. you're allowed to use a calculator in online applet, but you have to use it at the very last step. And if you say every step you wrote up until the very last step, and the very last step would be look up a table or an online applet and plug in answers. So that would be your last step. I mean, other than conclusion. So the graphing website is the, I mean, you should know that already. The tick is statistics.berkeley.tutor.java.html. Should be like something like that, and then you click the category distribution tab. Remember, you only have 3 minutes left, so be aware of that and don't submit it. Like it will close after 10:25. Or is that 10:25? Yeah, it will close after 10:25. Yeah, if you finish the quiz and submit it already, look at problem 1 and problem 3 from like section 1 discussion worksheet. Okay, it's 10:25 already, and I believe you guys are all finished on the problem. So um so for the discussion worksheet, let's move to the discussion worksheet. I mean I have already finished the review for the goodness of faith. So maybe we can start working on the problem. Let's work on problem 1 and 3. Um yeah. So problem 2 are pretty much the same thing as problem 1. And then like tell me your progress for doing problem 1 and 3. If you finish problem 1 and 3, work on problem 4, but we might don't have enough time to work on problem 4. So like depends on your progress. So first work on problem 1 and then work on problem 3 and tell me your progress. And if you have any questions, just don't hesitate to write it out in the chat. Yeah, so do the problem now. Yeah, and also like a lot of you haven't submitted the homework yet. If you did finish, like just don't forget to submit the homework. I haven't received too much homework right now. Yeah, and don't forget to update your progress. I believe some of you should already finish problem 1. Okay, if you finish problem 1, work on problem 3. I'll probably like talk about these 2 problems together. Okay, so let's talk about problem 1. Okay, my screen froze again. So problem 1 is basically similar to the problem I mentioned before your quiz. So the problem is that if you roll a die 60 times, it's so slow. So if you roll a die 60 times, you get 10 ones, 10 twos, 10 threes. So when we're reading this problem, you see that we're rolling a die 60 times, and then we're like checking if our a lot of like observations matches our expectation. That means like we're working on a chi-square test of goodness of fit. So that's where after you read the problem, you need to like write a table. I'm just saying like in general for this type of problem, you need to write the table that has a value observed frequency. Like directly after you read the problem, you should like it just like directly come into your mind and you can write it very quickly because you have a die. So the value is 1, 2, 3, 4, 5, 6. And remember what we are checking? We're checking that the null hypothesis is if the die is fair or not. If the die is unfair. So our observed value is given in the question 10, 10, 10, 2, 8, and 20. So in total of 60. Our expected value is because it is supposed to be a uniform distribution. So it's 10, 10, 10, 10, 10 for any possible value. So and then we need to calculate the difference square over expected value. And this is 10 minus 10 squared divided by 10 equal to 0. 10 minus 10 squared divided by 10 equal to 0. 10 minus 10 squared over 10 equal to 0. 2 minus 10 squared divided by 10. This is 6.4. 8 minus 10 squared divided by 10. That is 0.4. And 20 minus 10 squared divided by 10. That is 10. So yeah, I guess there is a huge lagging between what I wrote and what I said. So for now, like the degree of freedom is equal to the range minus 1. So we know that the range is 6 because there are 6 possible outcomes. So the degree of freedom is equal to 5. And our statistic is the summation of the last column. So summation of last column. So that's 6.4 plus 0.4 plus 10. So that's 11 or 16.8. So we have these two values. So we should be able to yeah, my earphone is also battery. Okay, so we have these two values and we should be able to compute the p-value. So we have two ways to solve this problem. The first way to solve this problem is just to look at the p-value. So remember, if we use a calculator, so we can use a calculator for chi-square, and we can compute the probability of R greater than 60.8. Remember that's our p-value. And if you do that, you will get this is approximately 0.01. But we know that our significant level is 0.05. So that means 0.01, the p-value is less than our significant value. And that means we can reject our null hypothesis and make the conclusion. Another way to solve this problem is to look at the critical value. Remember, like the critical value is the boundary of rejection zone. So if you draw a graph, this is your critical value, and that represents everything like on the right side is the rejection zone, the region for rejection. And you want to check if your p-value falls into not exactly p-value, if your like R statistic falls into, and check if R statistics fell into the zone. So the critical value is directly related to the degree of freedom of the chi-square and the significant level. So if you check table for significant value 0.05 and degree of freedom is equal to 5, you will find the critical value for this chi-square is 11.07. But we know that our R statistic is 16.8, so that's greater than 11.07. That means it falls into the rejection zone, so we can reject our null hypothesis. Is there any question about this problem? Like, I just don't know why the meeting is not updating. Yeah, there's a big lagging between what I wrote and what I said. Okay, so now let's move on to problem 3. For problem 3, we're talking about if so our null hypothesis here, after reading the problem, we know that our null hypothesis is our hypothesis that we claim that the coin is biased toward head at a rate of 75%. So that's different from like a fair coin. I'm claiming that the coin is biased, but it's biased specifically at 75% of towarding the head. And our null hypothesis is the coin is not biased at 75% toward head. So remember, in this situation, we only have 2 scenarios. It's whether a coin was flipped to be a head or a tail. So unlike the 6-sided die, we had like 6 situations. Now we only have head and tail. And then we write our observed graph, and observed value and our expected value. So remember, like we have 40 observations, 40 flips. And out of these 40 flips, we get 25 heads and 15 tails. But if we were to expect 40 tails, how many heads do we get? That's when we assume our null hypothesis is correct. So that's 40 times 75%, which is 30. So we're expecting 30 heads. On the other direction, we're expecting 25% to be tail. So that's 10. So how do we calculate difference square over expected value? That's just 25 minus 30 squared over 30, which is, I don't know, 25 over 30. And for the tail is 15 minus 10, observed minus expected squared divided by expected. So that's 25 over 10. So then we can calculate our R statistic. Our R statistic is just 25 over 30 plus 25 over 10. Remember that R statistic is just sum of the last column of our table. So that's 10 over 3. And what is our degree of freedom? Degree of freedom is the number of the possible outcomes minus 1. There's only head or tail, 2 outcomes. So 2 minus 1 is equal to 1. So that's our degree of freedom. So we can plug into the online applet, and we get that, or like we can check the table, the chi-square table. You can find the chi-square table online anywhere. That's good. We're given the significant level is 0.05, and our degree of freedom is equal to 1. That gives us the critical value, which is the boundary of our rejection zone, to be 3.84. So that means on distribution, 3.84 is the boundary of rejection zone. The shaded area are rejection zone. And we know that 10 over 3 is like 3.333, which is less than 3.84. So it doesn't fall into the rejection zone. It's somewhere here. So that means we cannot reject our null hypothesis. So we'll stay with our hypothesis that the point is biased toward 75% toward height. Is there any question about what we have here?
Zihao, I have.
Okay.
Can you hear me?
Yeah, I can hear you.
So for this problem, could we also have solved it using like the binomial distribution, counting like the number of successes from 40 flips?
The binomial distribution?
Yeah.
So what do you do? You calculate the binomial
like
probability?
We could, yeah.
Well, we're doing a chi-square test, right? We're not actually calculating the probability.
But yeah, if we were to if we wanted to calculate the p-value, could we also have done that as well? Would that also have worked?
Maybe like send me your progress of solving this problem, and I will take a more careful look.
Okay.
Okay. Because for now we will do something pretty exciting. So we will take a attendance, but in this attendance, I'm giving a survey, and in this survey we will, like, according to the result of this survey, we will directly do a hypothesis testing for testing of independence. Instead of doing any regular problem, we do the problem that we create just now. So let me start the pool and launch the pool. So you're gonna answer problem 1 and problem 2, and you're gonna give answer for problem 4 given the result of problem 1 and 2. So that's just like combination between 1 and 2. Whether your answer is true, true, or true, false, or false, true, or false, false. Yeah, and you have 2 minutes to do the thing, and then if you haven't do the course evaluation yet, you can answer it no, but I will do it now and do the course evaluation now. I believe there's a lot of students in my second section who complete the course evaluation, but for those who appear to be in my second section right now that are originally from the first section might not have do the course evaluation yet. So that might be something interesting. Okay, so my student told me that the poll disappeared for her. I have no idea how do I control this. So yeah, I don't know. I can't like restart the poll. People are already answering the thing. So I guess I would just mark you as being attending, but oh really? Yeah, so basically problem 4 is asking the answer of first 2 problems. So is it still not working for those of you who send me private message? Interesting. Yeah, since I guess no, like problem 4 are just like the answer for the first 2 problems on your poll. So you can just tell me that directly the yes or no. Like is that yes yes or no yes or yeah. I probably should state it as yes or no instead of true false. So yeah, it's a matter of yes or no. Okay, I will stay here for 1 more minute. So in this 1 more minute, those who haven't completed the course evaluation can send me or can do the course evaluation, and especially for those who are from the first section. Okay, so the problem was solved. Yeah, and I believe most of you have the problem. So Ryan, you sent me a private message. Can you like copy it to your email? I will reply to your email for this problem. Like I can't stop right now for answering your problem. So can you like send me an email and I will give you a more detailed explanation later. Okay, so let me end poll and show you the result of the poll. So here is the result we get. And then right now, that's the exciting part. Is that we will do a chi-square test of independence ourselves on what we have the information here. And I personally feel like this is very interesting and very cool. So for example, our null hypothesis is that we want to test the independence between if you are doing the course evaluation, you have completed the course evaluation finish, or versus are you feeling good about finals? So is there any relationship between these two? So our null hypothesis is that they are like independent. Where our alternative hypothesis is that they are dependent. So I want to do a chi-square test of independence that's different from goodness of fit. So for doing a test of independence, we look at two events. The first event is if you finish the course evaluation. So that's course eval. It has two answers, either yes or no. And the other event is feel good on final. That's also either yes or no. And for yes or no, we can have like observed value and expected value. We can also have like observed value here and the expected value. So here we can write the total at the end and the total here. So there are total 24 students in my class in this section who answered the poll. So total number of people are 24. And let's fill out the observation. We have 7 people who answered true and true. So who are finishing the evaluation and feel good on final. So that's great. And there are 8 students who said they finished the evaluation but doesn't feel good on the final. And there are 2 students who didn't finish the evaluation but feel good on the final. And there are 7 students who are didn't do the evaluation but not feel in the not feeling good on the final either. So let's calculate the total value. Total value here is 15 and total value here is 9. Total value here is 9 and total value here is 15. So remember, in a test of independence, how do we calculate this value? This value is calculated by the total in this row, so this value, and the total in this column, so this value, and the total number of population. So this value is calculated as 9 times 15 over 24 here. And why do we get this answer? It's because so the expected value here for yes and yes is theoretically a joint distribution of answering yes and answering yes on 2 questions. So answering yes on course evaluation here, the probability is 9 over 24. And answering yes for feeling good on finals is 15 over 24. But these are the probability of answering yes on both questions. And we are talking about the expected value. So expected value here is NP. It's 24 times the probability, which is 9 over 24 times 15 over 24. So here our expected value is 9 times 15 over 24. That's exactly what we get here. So we can do the same thing on the other 3 spots. So here will be 9 times 9 over 24. And here will be here will be 15 times 15 over 24. And here will be 9 times 15 over 24. So now we want to calculate the R statistic, and the R statistic is the summation of observation minus expected value squared over expected value on all this 4 events here. So our observation here is 7 minus 9 times 15 over 24 squared over 9 times 15 over 24. So that will plus 8 minus 15 times 15 over 24 square over 15 times 15 over 24 plus 2 minus 9 times 9 over 24 square over 9 times 9 24 plus 7 minus 9 times 15 square over 24 square over 9 times 15 over 24. So let's quickly calculate the value by using a calculator. So that's 9 times 15 divided by 24, which is 5.625. That's over 7 minus the value, which is 1.375 plus 15 times 15 divided by 24, which is 9.375. And we want it to be minus by 8, which is also 1.375. And we want the third value to be 3.375, and that's minus 2. So that's again interesting. 1.375 squared plus 5.625, 9 times 15 over 24 minus 7. Okay, so that's very interesting. Everything on our fraction is 1.375 squared divided by something. So let's quickly calculate the result of that. So that will be 1.375 times 1.375, which is 1.89 times 1 over 5.625, which is 0.178 plus 0.178 plus 1 divided by 9.375, which is 0.107 plus 1 divided by 3.375, which is 0.296. So we can calculate the value 0.178 plus 178 plus 0.107 plus 0.296 times 1.89 is 1.43. Okay, finally, we get our value of our statistic. So all I'm doing is I calculate the expected value, and then I do a summation over the observation minus expectation square divided by the expected value. So we get our R statistic. And then what we need is the degree of freedom. So remember, for degree of freedom for test of independence, it is A minus 1 times B minus 1. So that's exactly the third problem on our pool, which is false because they're kind of like reversed for two different tests. So here is 2 minus 1 because there's two possible answers, yes or no, for both problems. So the degree of freedom is 1. So right now, let's go to our online applet, and we input the degree of freedom equal to 1, and we input the endpoint, which is 1.43, and see what's the result. So the result of the p-value is, so that's the distribution here, and it gives us the probability of R greater than 1.43 is, so this is 1.43. You can also plug this information on your own device. So it's 1 minus, it gives this area to be 0.768. So the p-value is 1 minus 0.768, which is 0.232. But this is greater than our significant level, which is 0.05. So on a graph, our significant value will be somewhere here, which gives you a significant area of 0.05, but our p-value is here. So our p-value doesn't fall into the rejection zone of our significant level. So we can draw conclusion that we cannot reject our null hypothesis, which means that we will stick with our null hypothesis that the answer for you completing your course evaluation is independent with you feeling good about the final. So isn't that really cool? Like tell me if you feel that's cool. So I personally feel that's really interesting because instead of working on specific type of problem, we're devising a problem of ourselves and we're like solving this problem. So I hope this example sparks your interest on doing the hypothesis testing. Okay, thank you guys for saying this. I feel very glad that you guys are interested in that. So yeah, so like this example tells us what, like you don't have to like in your own life, you can just like send out surveys to people and then it directly tells you if two events are independent or dependent with each other by doing a simple chi-square test. So I hope you know that what we learned is it's not just something that you have to do the problem solving. It's actually very useful in your life. And actually it is very common if you do research in different fields. For you, maybe in MCP in biology, to say if two events are independent or not. And so again, that's very cool for doing this problem, but for your own final test, you still need to do the problem correct instead of doing fancy work. So what I would recommend is to look through the homework very carefully and look through the solutions very carefully, and then try to mimic each step what the homework solution are telling you about. Because generally the rubric for final will be the same as what we have, when we provide you the homework solution we provided to you. So as long as you follow the procedures for the homework solution, you should be able to get a perfect score on your final exam. So that's for problem solving, and what we have here is fancy problem. And on Thursday, since we don't have too much information, I believe we will still have like time to cover more about problem solving on chi-square test, especially tests for independence. So again, I hope you guys are interested in this topic. I actually like deliberately think about how do I manage the time for this class and writing the problems. Yeah, I mean, if you like it or you feel like I'm doing well, so maybe like for those who haven't do the course evaluation, do the course evaluation. And otherwise, yeah, if you have any question, feel free to email me or attend my office hour. And otherwise, feel free to leave. I will stay here for 1 more minute to answer some like quick questions. And then I'm gonna end the meeting. And if you didn't like follow what I mentioned here for the last test of independence, I have already recorded this video, and you can always like go back to YouTube online to re-watch it. So if you have the ability to do it by yourself, like to devise the experiment and to do the experiment and get the result by yourself, that means you perfectly understand the hypothesis testing of chi-square. Yeah. So feel free to like devise your experiment on yourself. Yeah, I don't have too much information to mention. So if you don't have any questions, just feel free to leave the chat room, leave the meeting.